Okay, good morning, everybody. I think we can start. Let's say a short comment on the projects. You can find on the Dropbox this table in which I already assigned the project as specified in the project rules. I usually take more time on the rules to make sure that I'm able to assign everything. Also, I obviously also have the names, but I usually published all documents without name, only with the register numbers. I delivered the first choice to almost every group, but 3 of them that took the second choice. And essentially, I did that because following the first choice, something like 19 students, 19 groups out of 24, 19 groups out of 24 selected my project, and only 5 groups selected Professor Cabodi's project. So I tried to balance a little bit, so I assigned a second project in all groups that make the selection not in the first part of the list, in the ranking, and selected as a second project a Professor Cabodi project, such that at the end of the day, Professor Cabodi is in charge of 8 projects, and I'm in charge of the remaining 16, which is a lot, but okay, I hope this is gonna be okay. You can take a look at that, and if there is any problem, just contact us, and we'll discuss about that. Otherwise, you can start working at your project. And by the way, one extra comment that I will try to clarify a little bit better during the last week. 2 years ago, I was able, actually last year, but it was for the student of 2 years ago, I was able at the beginning of February, so at the end of the section, January section, and before the beginning of the course, to organize a trip to Canelli, to the Harold group, to the main production site. The idea was the following one. The students that had sold one of their projects represent the project to them, to the human resource office, to the human resource personnel, to the technical personnel, technical personnel. They took us there, so we met in the morning, just close to here, close to the parking spot for professors. They took everybody with a bus, so we went to Canelli. There were all those presentations from the groups that work for there. They gave their own presentation. Then there were private discussion about what we are looking for a job, what we are looking for as a new employees, and stuff like that. And we came back in the afternoon. So I'll show you, maybe again during last week, there is also a page on the Harold group discussing about Harold group meets the Harold group meets Politecnico of Torino students. Unfortunately, this year, that is in this February, we were unable to organize this trip because there were too few students that were able to make the trip, to take the trip. So we'll talk again about that. If you don't end your project too late, and if you want to have this opportunity, that is visit them firm, taking a look at what they do, taking a look at the problem they have, and so on and so forth, that can be something that I offer you, even with, let's say, several months of delay that is after the course, because the idea is for you to present the project again. After I gave you a mark, you can represent the project to them, so you can, in a way, show you to them. They can like what you said and maybe offer you a job or an internship or whatever. And so that's why I usually organize that after the project has been completed. But the project has to be completed not too late, because otherwise it's impossible to organize to know how many people, how many students are willing to participate. And there must be enough students to participate, because they, again, organize a trip with the bus, lunch for everybody, the visit to the sites for everybody, explanation of the machines, and so on and so forth. So 2 years ago, there were 20, 25 students participating. This year, the number of students were much smaller, so we decided not to do that. So keep that in mind. If you work on a project, you have this possibility that I will offer you in a few months. And obviously, the sooner you end the project, the easier it is for me to understand whether you want to participate or not, because obviously everything logistically depends on the number of students participating. And okay, keeping this in mind, and we'll talk again maybe next week, in 2 weeks' time, and maybe when you end the project. Once said that, questions on that? Okay, once said that, the target today is to analyze, possibly entirely, the first section of Unit 8. So in a way, yesterday we ended up the lesson half an hour before, the end 20 minutes before. Today, it may be the case that I may be overflow, run out of time a little bit. I don't know, it's the first time I introduce this section to you, to system and device programming students, so I don't know my speed, so we will see. So the idea of this unit is to, once we have seen together, sorry, let me check, okay. Once we have seen together two parts of introductions, a general introduction to parallel computing and a more specific introduction to GPUs and CUDA programming. And now we have to understand how to write our small first program. Okay, so the idea is to show you three different programs of increasing size, the basic concept of writing a CUDA program, which, as I mentioned, is not that difficult at the very beginning. So that's the target today. So what is CUDA? CUDA, as I mentioned, CUDA is a sort of language that has been introduced to use as efficiently as possible NVIDIA GPUs, and is essentially based on C and C++ with small extensions to enable heterogeneous computing. Heterogeneous computing means that, as I mentioned yesterday, when you write a CUDA program, part of the program is manipulated by the CPU, and part of the program is run by the GPU. And CUDA, at the very beginning, is straightforward to use, and the system calls are easy to use to manage the device. So as I mentioned yesterday, the terminology I will follow is the following one. Every time I refer to the host, I refer to the CPU and possibly to the CPU memory, so the host memory. Every time I talk about the device, that's why that's device programming. For the first time I introduced this part, so for the first time I really can say that this is a device system and device programming course. The device is the GPU and possibly its memory. That's because, again, the code is written in the same source file, and the compiler distinguishes between the host code and the device code, such that each one is running its own code. So that's the more, let's say, defined idea. We write an application. There is a further example after this slide. We write an application in which we, in C++, obviously, including CUDA primitives. And in this and the following page, I indicate with serial code the code running on the CPU, and with parallel code, the code running on the GPU. That's not strictly necessary, because even on the CPU, you can run parallel code. Because you can run the CPU, on the CPU parallel code that is running other parallel code on the GPU. But to differentiate in this and the following line, I call serial code the code which is running on the CPU, on the host, and parallel code, the code which is running on the GPU, the device. Why do we need something running on the CPU? Because usually it's the CPU to prepare everything for the GPU. So for example, is the CPU performing, I don't know, some sort of input or some sort of output? Is the GPU passing the data to the GPU, the data on which the GPU have to work? And as the CPU, which at the end get the results and use the results and present the results to the user. So in a way, there is a sort of preamble, sort of premises section and the prologue section in which the CPU is activating the GPU. Then we have a part in which, so this is the preamble. Then during the GPU, when the GPU is running, also the CPU can run. So we can have the CPU running in parallel and the GPU running in parallel with many, many threads. So the CPU running with a few threads, with a few core, using a few core, and the GPU running with many, many cores in parallel. Obviously, the threads within the CPU must synchronize, must have the necessities of synchronization, but also the threads within the GPU must have the necessity of synchronization. At the end of the day, they have mutually synchronized, such that the CPU has to wait for the CUDA program to end, for the host, for the device to end, and get the results. So in a way, again, the CPU is running its own code, preparing everything and getting everything from the GPU. And GPU is running its own code, executing all the threads it possibly has on the data set, the CPU database the CPU has prepared. So if you want to see the thing a little bit more into the detail, that is already a CUDA program, a complete CUDA program, in which you see I'm using C++. I know that now it's difficult to read, but we'll see more detailed examples, in which I'm using C++ with some specific instruction that are in CUDA language. So at the end of the day, the CPU is preparing what the GPU needs, let's say serially. Then it runs the GPU, in which we run parallel code with many, many threads. We synchronize with the execution, and we display the results. That's the easiest possible formulation of a CUDA program, okay? We set everything for the GPU to run. We run the GPU. We wait for the GPU to end. We get the result from the GPU, and we display the results from the GPU. That's why we have a certain level of let's say, overhead that must be controlled not to run much slower than the original sequential or parallel CPU program. Okay, essentially, the process can be divided into 3 sections, as I mentioned. This is the first section. We have the CPU on the left-hand side and the GPU on the right-hand side. They communicate using the bus. And in the first phase, part A, the CPU prepares the material for the GPU and copy the memory from the data from the memory host to the device host, to the memory device. So data are transferred from the CPU memory to the GPU memory. This transfer is usually expensive. I will talk a little bit about that in a few slides. Then we have the phase in which the GPU is working on the data I passed, doing whatever it has to do. For example, the matrix multiplication or the machine learning, I don't know, whatever complex computation. And finally, there is a third phase in which the results are passed back to the CPU, which can use it and eventually display it to the user. So before really see in the first example a few more comments. As you have seen, phase 1 and phase 3 imply data movements from the host to the device and then from the device to the host. Often, those two phases are the bottleneck of the procedure. What do I mean? I mean the following. Let's take an example that is written here at the bottom. For example, if I want to add two arrays, I have two very long arrays, V1 and V2, and I want to generate V3. Obviously, I can use a GPU because I can run probably as a number of cores that is equal to the number of elements, such that instead of having a linear cost to compute the sum, I can have a constant cost because each thread is just dealing with one single element. But at the same time, I have to copy the array from the CPU memory to the GPU memory. And this is a linear cost as well. And then I have to copy the resulting array from the GPU memory to the host memory. And this has a linear cost as well. So at the end of the day, instead of having a linear cost, that is the one to compute the sum, I have two linear costs to compute the array forward and backward, plus one constant cost. And obviously, I usually is lower. So in a way, this bottleneck can be bypassed only when operations are complex enough. For example, if we perform a matrix multiplication has a complexity, an asymptotic complexity, which is cubic in the size of the matrices. So in this case, the linear cost of copying the matrix forward and backward can be balanced by the constant cost to compute the product, or smaller cost, linear cost to compute the product. Notice that, by the way, the example number one I made just now, that is adding to array, is the third example I'm going to present today. So in a way, it's an example that I shouldn't present, but I use exactly that example because I need to explain you a few things, and that example is the simple case in which those few things can be applied, can be, in a way, exercised, okay? Questions? Okay, what do we run on a GPU? Usually, on a GPU, we run the so-called kernel. A kernel is a function, a specific function. As we run a thread, when we run a thread or when we run a task, we usually run a function. Now instead of running a thread or running a task, which is then associated to a thread, we run a kernel, which is again a function, which can possibly be associated to thousands of threads in an automatic way. Automatic way means that each thread has to have the power to know which thread is it. So which one is in the group of threads, on which data it has to work. Because if I run in thousands of threads, and each one has to work on a specific pixel of my image, or on a specific element of my matrix, or on a specific element of my array, each one has to know somehow automatically on which element it has to work. Otherwise, it gets too complex to specify for each of them what they have to do. So each thread run through the kernel may work independently or uses some level of synchronization with the other threads on specific part of the data set, the database. And that's the first program you see in CUDA language. And as usual, as in many other cases, is the so-called hello world program, which has the only purpose to display hello world. The only difference is that in this case, instead of displaying just one single hello world, we can print out thousands of hello world. So thousands of printing of the same, let's say, message. As you can see, this is a CUDA program because I have a CUDA extension in here. So we have no more C++ file, we have CUDA file that can be compiled using MVCC. And then we have several parts, essentially two in this case, because the program is very simple. The kernel, which is the CUDA function, and the main, which is the part setting up everything. So the idea is that, to summarize, we have a kernel, which is what is run by the GPU. We have an initial part in which the CPU is setting everything for the GPU. We run the kernel, that is, we run the GPU. We synchronize with the GPU, and we end. So again, I try to repeat. The first part is the one in which decide how to run the CPU, how to run the GPU. Then we run the GPU. Then in here, we can work in parallel. The GPU is working, we can do something else. And when we have done, in a sequential or parallel way, we wait for the device, CUDA device, to end. So we synchronize with the CUDA kernel, which implies that the CUDA kernel is done, which implies that we can use the results. In this case, there are no results, just printing messages, and we end. In this case, we end. Otherwise, we do something else. Once we have this program, we can compile it in this way, and we can run it in this way, and we receive the message hello world from a GPU, in this case only once, and I will explain you why only once. It depends on those values, but we have to understand what those values are. But before understanding those values, let's start to understand how to write the kernel function. Question? Okay, first part, what's the kernel function? As you can see, the kernel function is more or less a standard C or C++ function, with specific, let's say, keyword to identify it as a kernel function. More specifically, you see a double underscore in here, and the double underscore in here with the keyword global. The type is void, which implies that this is a kernel function. So it's a function which is run by the GPU. We can have parameters in here that are passed in there. But we have no parameter for this function, so we have no actual parameter in there. We are not passing anything. For now, we ignore that. I will explain that next slide. So this is a standard function in which we can do whatever we like to do. In this case, we do almost nothing but printing a message. So we print a message and we end. If we run 10,000 of those, we have 10,000 of those printing a message, theoretically with some sort of interleaving between the threads. So we should protect the writing part, but that's a little bit too advanced for now. But we print everything on the screen. And at the end, we end. Again, notice that the NVIDIA compilers divide the code such this one that is run by the GPU, and the other which is run by the CPU automatically. So theoretically, if there is nothing for the GPU, NVCC compile everything for the CPU. Okay, so now how can we run this kernel function, which is very, very simple? We run this kernel function as I show you in here before the synchronization, including those 3 lines. Line number 3 is essentially easy enough because, again, we use a specific notation, triple brackets in here, a triple brackets in there, to indicate that we are running a CUDA kernel with this parameter and with this size that are specified in here. Grid dim is this one, block dim is this one, and those 2 objects, those 2 variables, predefined variable, are of type dim3, which implies there are essentially 3-dimensional objects as they are three-dimensional objects, they have 3 dimensions. And obviously, we have to specify what do we mean with that. And that is explained using the next slide, in which, for the sake of understanding, instead of 1, 1, 1, I put different numbers. So in a way, when we run a kernel, we run a grid of blocks. And in each blocks, we run a certain number of threads. So essentially, we run a grid of blocks of threads. Each grid can have a 3D shape. Each block within the grid can have a 3D shape. So we can have a 3-dimensional grid with 3-dimensional blocks, which imply that for each block, we have a 3-dimensional set of threads. For example, in this case, I define the grid. And when I define the grid, those are the block sizes. So I have 4 blocks on the x-axis, 2 blocks on the y-axis, and 1 block on the z-axis. Every time I have 1 in there, it implies that that dimension is not used. So theoretically, if I want just to use a single dimension, I put a 1 in there, and I have only this one. If I put a 1 in there, I have only this dimension, which also implies that when I put 1, 1, 1, I have only 1 dimension, 1 size along x, the x-axis, 1 along the y-axis, 1 along the z-axis, which implies that I have a single block. And this block is made up one dimension on the x-axis, 1 along the y-axis, 1 along the z-axis, is made up by 1 single thread. So in the previous case, which is this one, I run 1 single block containing 1 single thread, which implies that I have just 1 message, which implies that it was useless to use the GPU, okay? That was an example. Now, instead of using 1, 1, 1, I'm using 4, 2, 1, which implies that I have 4 blocks on the x-axis, number from 0 to 3, 2 on the y-axis, number from 0 to 1, 1 on the z-axis, so I do not have the 3rd dimension. And for each of those, I have 4, 3, 2, 4 threads on the x-axis, number from 0 to 3, 3 on the y-axis, number from 0 to 2, and 1 that is no z dimension. Okay? Which implies that in this case, I run 8 blocks, each one containing 12 threads, 8 times 12 threads in parallel. Okay, 96 threads. So in this case, I run this kernel, that is, I run this function, 86 times. 96 times. 96 times. I run this thread, I run this function 96 times. As easy as that, okay? Questions? Again, notice that there are no dim2 and dim1 objects. If we want dim2 or dim1 object, we just put 1, or we just put single value in here. It's also acceptable to put 4 and 5, which implies that the grid has a 1 dimension, single dimension, also the block has 1 single dimension, and avoid defining those 2 objects. But generally speaking, this is the general case. I define those 2 objects, but at most 3D, but they can be 2D or 1D if I put a 1 in the dimension. And then I use those 2 variables to run the kernel. Again, is there any question? Question from home? Yes, there is one question in there. It's about the project, so maybe I'll talk at the end of the lesson. Questions? Yeah. Is there any relation? Yeah, obviously there are limitations. I'm gonna talk about that. You cannot run a grid of 10 million elements along the x-axis and so on and so forth. And unfortunately, those limitations strongly depend on the GPU you are using. And that's one of the difficulties. So you cannot, generally speaking, just programming a generic GPU. You should program your own specific GPU to obtain the maximum efficiency. Okay? Because obviously, in a way, one of you can tell, but why do we need 3 dimensions? We could just have 1 dimension. We put 1 million in there, 10 million in there. It's easier. But obviously, you know that in many cases, we can have 1D problems, but we can have 2D problems, and we can also have 3D problems. For example, if we work on a screen, we automatically have 2D problems. So it's better to specify a 2D problem as a 2D problem instead of to 1D problem. So the passage from 1 dimension to 2 dimension, or from 2 dimension to 2 dimension, it's possible. I will show you how to do that, but it's easier if we have the possibility to use up to 3 dimension. Okay, anything else? I cannot hear you. Well, theoretically, we should protect the printing function. But again, I avoided to show you that because that implies using CUDA synchronization feature, which I haven't seen yet, and maybe we just partially see for the lack of time. But at least I show you one synchronization function, which is this one, which is the main one, stopping the CPU and letting the CPU wait for the GPU to end, such that the CPU is stopped by this. When the GPU ends, it starts again using the results given by the GPU. So this is already a synchronization function, but for now it's the only one. Okay, a few more comments before moving from, let's say, example number 1 to example number 2. Okay, as I said, we can run, as I just showed you, we can run in a grid many blocks, and each block many threads. Let us suppose that those threads want to deal with pixels in a screen. Obviously, each one should know which piece it has to manage. It should know that more or less automatically. So in a way, there is a bunch of variables that automatically specify everything a thread may need to understand who it is. And those variables are predefined. We have basically four objects, 4 variables. The dimension of a grid, which is defined, the one I define in here, which is predefined, specify the number of blocks within the grid in each dimension. Then I have the block dim, again, which is predefined. It specifies the number of threads within each block. Then we have the so-called block IDX identifier that has 3 indexes, .x, .y, .z, that specify the position of the thread within the block. Specify the position of the block within the grid. And then we have thread IDX identifier .x, .y, .z that specify the position of the thread within the block. So in a way, we have the grid size in terms of blocks, the block size in terms of threads, the block position within the set of blocks, and the thread position within its block. And to understand that a little bit better, obviously, I have to show you how it's possible to use those 4 variables to identify yourself, with an example in which more or less everything is the same, but the kernel function. And in the kernel function, instead of printing the message hello world, I'm printing a set of values, which are the blocks IDX along the x-axis, along the y-axis, along the z-axis, and the thread IDX along the x-axis, y-axis, and z-axis, which imply that those three values specify the block in which the thread is. And those three values specify the thread position within that specific block. Are you following? So in a way, I can run the program in this way, like before, in which I just print those information, this information at the kernel thread, and then at the end, after synchronization, I display all parameters that are the grid dimension along the x, y, and z axis, and the block dimension along the x, y, and z axis. And if I run this program, I should get something like that, in which I have a bunch of messages, in which I have the three values, starting from 0, 0, 0, 0, 0, 0, 0 to 310 because I have 4 to 1. The maximum is 310, and 3 to 0 because I have 4, 3, 1. So the maximum is 3, 2, 3, 2, and 1, 3, 2, and 0, 3, 2, and 0. In here, I put the threads in order, okay, more or less in an increasing order, but this is not the case. Obviously, when I run all the threads run each one at its own speed. So you can have different versions of the display depending on the speed of the thread. And if you want, you can grab my program. My program is in the exercise directory. I hope I have copied it. You can grab it, copy it on the portal I mentioned, run it, and you see this sort of output. And at the end, you see that the block size was 4 to 1, this one, and the grid size was 4 to 1, and the block size was 3 to 1. Okay? So in a way, this example shows that each thread knows the coordinates of the block in which it's running, to which it belongs, and the position, its position within the block. Is that okay for everybody? Questions? Sure? Okay. So in a way, again, a kernel is executed as a grid of blocks. Each blocks run a specific number of threads. Threads within the same block share data memory space. So one of the questions, again, that was already made is, why do we just focus on 1D and not on 3D? For two reasons. First of all, we don't have an infinite capacity in each dimension. And secondly, the threads belonging to different blocks have different features. So for example, in a block, threads can cooperate with each other by synchronizing their execution and sharing data in the shared memory. So threads belonging to the same block can more efficiently communicate and synchronize between themselves, whereas threads belonging to different blocks cannot generally communicate or synchronize between themselves. So depending on the problem at hand, you may want to put more thread in a block or make blocks smaller and using more blocks, depending on the level of synchronization and level of communication threads may have. Because threads, again, in different blocks usually cannot cooperate. So there are differences in having blocks, even a grid of blocks of threads. Again, blocks and grids and blocks can have 3D, 2D, and 1D sizes. And this simplifies memory addressing when we deal with multidimensional data structure. But obviously, as I'm going to show you, we can always pass from a multidimensional data structure to a single one-dimensional data structure. The way is usually done by the C compiler dealing with multiple metrics, multiple dimensional metrics. As I mentioned already at least once, I think, even with you, if you define in C++ or in C a multidimensional matrix, a 2D matrix, a square matrix, you already know that the square matrix is going to be stored in your main memory, and your main memory is a linear sequence of cells, so it's an array. So in a way, you have to automatically perform a 2D to 1D conversion. And even if you define a 3D matrix, that 3D matrix is again stored in one-dimensional structure, which is the linear set of cells. So in a way, this sort of passages from 2D to 1D, from 3D to 1D, are common in other situations, and are common in here as well, because you can pass from 2D to 1D and from 3D to 1D, the way I'm going to show you in the next examples. Before, as being asked about the limitations, the number of all numbers depends on the GPU you have. The number I'm presenting now are going to be old tomorrow, or already old if you use very expensive GPUs. But the idea is that you have a number of stream processor from 1 to 100, a number of concurrent threads for stream processor in the order of 1K or 2Ks, and more specifically, which is important, a number of blocks up to 64Ks, and the number of grids up to 64Ks. So you can use at most 64Ks blocks, each one with 64Ks threads, okay, which are 2 to the power of 16 million threads, okay, something like that. Okay, that should be clear after my explanation, but I want to highlight that. Host and device memory are separate entities. So in a way, as I mentioned, theoretically, the CPU has to copy its memory, its data set from its memory to the GPU memory, and at the end, you have to copy back the results. So there are specific functions to move memory forward and backward, and in the third example, I will show you that. And there are CUDA API that allow to perform on the GPU operations that are very similar to the one usually performed on the CPU, like memory allocation, memory free, copy memory, and so on and so forth. Obviously, I should like to make a full list of those, but we are running in a way out of time, so we just see a few of those. And essentially, we see a few of those with the first example I mentioned before. We should have, that shouldn't be implemented on a GPU because it has a linear cost. So again, we need a linear cost to copy V1 into the GPU, another linear cost to copy V2 into the GPU. Then we have a constant cost, and then another linear cost to copy V3 into the CPU. So we have 3 linear costs instead of just 1 linear cost, that is the one performing this loop sequentially. So in a way, this parallel program is far more slower than the sequential original CPU program. But it allows me to show you how to better use those variables that so far we have just displayed. So, okay, in this case, the CUDA kernel is the following one, and I'm running it in this way. Then we see the framework, okay, how to deal with all remaining part of the program. But before going into the detail of the program, let's focus on the most important part, how to run the kernel and how to write the kernel. So we run the kernel in this way, and we define the kernel in this way. Now you see that we have grid size and block size, generically speaking, but we also have the parameters because we have the array V1, the array V2, and the array V3 that are these 3, okay? So I'm passing the 3 array. I'm passing the size, the grid size in terms of blocks, the block size in terms of threads. But then I have 3 cases. I show you 3 cases. In the first case, we have only blocks. So we have only blocks. We have a number of blocks equal to the array size, and 0. So we have only blocks and 0 threads. In the second case, we have only thread and 0 blocks. And in the last case, we have both of them. Why is that? Why do I show you those examples? Because obviously, depending on what we have in here, what we receive in here, when we define the function, we have to access the correct element in a different way. So again, let's try to make a step backward. I'm running a thread, which is supposed, I'm running a bunch of threads, which are supposed to add all elements of the array in this way, such that each thread is computing the addition of one single element. Okay, so each thread is just computing one sum. But obviously, each thread has to understand which sum it has to compute. And depending on how I run those threads, they have to understand their position, their order in a different way. So if I have only a size at the block level, the block is 1D, and I can use block idx.x, because it's the only dimension, in all 3 array as index, which implies that each thread will sum the element corresponding to its position within the grid. Okay? Obviously, I suppose that this array size is not larger than this 64K. Otherwise, I cannot run this way. Let's say array size is small enough. Okay? What about if instead of running only blocks, I run only threads? Well, I can use thread idx, one size, 1D, dot x, dot x, dot x. The index is the position of the threads within the block of threads. There is just one single block, so the position of the thread is given by its coordinate x. Okay? Obviously, what about if I'm using both of them? So if I'm using something in here and something in there, let's say only 1D. Okay, I have one value in here, less than array size. So I put part of the array size in the grid dimension and part of the array size in the block dimension. Then I have an index in here and also an index in there. How can I compute the overall index? Well, I have to do something like that in blue, in which, given the block index along x, given the block dimension, and given the thread position along x, I compute the position, the global position, that's the global position of the thread within the block of threads. Obviously, if I have a certain number of blocks with a certain number of threads each one, let's say n and m, I have a total of n times m threads, and n times m can be larger than array size. So I have to verify if I'm overflowing the array size, I don't have to compute the sum. Otherwise, I compute the sum. Okay? But what about this? So let's try to understand this a little bit better. This can be explained in the following way. I have the grid size, one dimension, and the block size, one dimension. Let's suppose that I have 4 blocks, each one of 8 threads. So I have the first block, the second block, the third block, and the fourth block with index x0, 1, 2, and 3. Okay? Within each block, I have 8 threads. So this is 8. I have thread 0, thread 7, from 0 to 7, from 0 to 7, from 0 to 7, from 0 to 7. So at the end of the day, I have 4 times 8, 32 threads running. So how can I know which one I am? I'm using this formula, which I say, okay, block IDX, which is my block position, times the block dimension, plus the offset within the block. Let's make an example. That's the example. Let us suppose that the block IDX is 2, so I'm within this block. And the block's dimension is 8, as I said before, 8, 8, and the thread IDX is 5. Let us suppose that is 6, actually. It's 5, but is in position 6. So if I compute 2 times 8 plus 5, I get 21. That is the position of this thread. So again, this formula for 1D blocks, for 1D grids or 1D blocks, gives the absolute position of the threads within the bunch of threads I'm running, which allow me to define the element of the array that that specific thread has to manage. Is that okay for everybody? Why? What? Why is not possible? So why do I have constant value in here? So why do I have 8 and 4? Is that the question? Yes. This is the this is the this parameter. Yes, this is this parameter, which I fix this. This is the size of each block in terms of number of threads. Well, it's a number, so the question is this a constant value? Is the value decided when you run the kernel? So those values, this is just an example. I said 4 blocks, 4, this is 4, 8 thread, this is 8. So I should rewrite that with 4 and 8. Those two values, as I showed you before, are defined when you define, I have to move back, the grid dimension and the block dimension. So when you define the grid dimension and the block dimension, you define the configuration, the grid shape, and within the grid shape, each block shape, in terms of threads, you are using to solve the problem. And this is just an example in which I have instead of only blocks or only threads, I have some blocks and some threads, more specifically 4 blocks and 8 threads. So I have to move from the block index and the thread index to a global index, because at the end of the day, I want to use this IDX, as I mentioned, to compute the sum in here. So you have to linearize those two values into a unique value. Okay? Anything else? And obviously, this is just the easiest case, because in this case, again, I just use a 1D block or 1D thread. And this can be generalized, and I'm going to show you how, because we can have 2D blocks of 2D, we can have 2D grids of 2D blocks, and we can have 3D grids or 3D blocks. And also in those cases, we may want to pass from the set of 3 indexes to a single unique absolute value position within the set of threads. But before moving, any question? Okay, so now we have understood more or less how to call the kernel and how to define the kernel. Let's try to understand the entire program, how it's going to work. So again, the target, don't forget that I want to do that operation, okay? That's my target. And obviously, again, it's not the right problem to show you, but that's the easiest one to start with explaining this concept. So we have seen how to call the kernel, how to define the kernel. Now we have to define the entire program, which implies that we have to allocate the tree array on the host, on the CPU, and also on the device. We have to read the tree array on the host or set values in them, and then transfer the arrays to the device. We have to run the computation. We have to transfer the result back, and have to free everything and display the results. So if we want to see the entire program, that's the entire program. Okay, we have a bunch of definition, among which a few for C++ and this one for CUDA. Okay. Then I have the array size, which is small value for the sake of, let's say, experimenting without waiting too much. Then we have a function which I do not talk about because it's just a different version of, let's say, a random function generation, which set all the value within the array. So instead of setting manually 1024 values in the first array and 1024 value in the second array, I just generate those array randomly using this function. After this function in here, I have the CUDA kernel, which I do not report anymore because it's the first, is the one we saw before, that is this one, okay? So this one is in there, I say space. And then I have the main. So what do I do in the main? Step number one, I define the array in the host memory space. Step number two, I randomly initialize those arrays using the function we saw before. Init array is the previous function, the former function. Okay? Then I define and I allocate the tree array in the device memory space. And you see that the CUDA malloc is somehow similar to the C malloc from which it originated. So I define the tree array. I have a pointer to float. I get the pointer to a pointer, which I transform to a double void star object. So I can be generic. This is the array size times the size of a float. So the total quantity of memory I have to allocate for V1, V2, and V3. Now I have the memory allocated in the host CPU. I have the memory allocated in the device GPU. And I have to transfer. So I transfer my step number 4. My step number 4 is to transfer CUDA memcopy host to device from the host to the device. This array to this array, this quantity of bytes for V1 and for V2. Okay? So to summarize, I define the array in the CPU space and I initialize them. Then I define the array in the host, in the device space. Now I copy the content of the array in the GPU space. And now I can run the thread, I can run the kernel. In here I run the kernel, but obviously I have to define those two parameters. How can I do that in practice? Obviously, everything depends on this value and on my CPU. So in this example, you can do something different. In line number 5, I define a size equal to 256. That is the block size. So I define a block size of 256. So I have 256 blocks. I decided this way, okay? Obviously, as I have to deal with array size element, I have to deal with array size element. The number of threads within each block has to be such that, considering the number of blocks, I cover all the elements. So what do? I grab array size plus size minus 1. I divide that by the size, and I get the grid size. Why do I do plus size minus 1? Because if I had, for example, 1023 elements, 1023 elements divided by size, 256, in the integer field is 3. But to deal with 123 elements, I need 4 blocks. 3s are not enough. So you have to get the ceiling of the, I have to approximate, I have to get the ceiling value of this division. And to get the ceiling value of this division, I, in this case, sum the size minus 1, which is 1024 plus 255 divided by 256, which is 4. So you have 256 blocks of size 4. Actually, the contrary. 4 blocks of 256 threads, okay? And once I've done that, I can use the function we saw before, that is, given the blocks IDX, the blocks dim, and the thread IDX along the x-axis, I compute the overall position of the thread, and I compute the sum of everything. Questions? Any question from home? What else? Obviously, I have now many, many threads running. I can do whatever I like myself. In here, the CPU can run in parallel with the GPU. It can be parallelized as well. So I can have many threads running on the CPU. But at the end of the day, sooner or later, I will have to wait the results from the GPU. So I synchronize. And once I synchronize, so that's step number, this is step number, let's say, 5. This is step number 6, I synchronize. And in step number 7, I copy the results back. The results is in V3. I copy V3 in HV3 of this number of bytes. Now I have the array. I can display it, step number 8, and I can free all the memory I allocated before, step number 9. Questions? Sure. Okay, as I said, this is a, let's say, very simple example. And at least I'm not going to I do not have enough time to go deeper in all those, let's say, aspects. But at least today, one more consideration is in order. That is, how can we manage multidimensional grid and multidimensional block? And the following slides try to show you that. So let us suppose that we have a 2 grid of 2D blocks. And we have something like that. We have, you see a grid, that's the grid. That's the grid, 2D grid. And each block is 2D. So we have several blocks on the x-axis and several blocks on the y-axis. And for each block, I have several threads on the x-axis and several threads on the y-axis. So in a way, we can use a bunch of formula to move from those block IDX dot X, dot Y, and dot Z, and thread IDX dot X, dot Y, and dot Z to a unique global index of the threads. Let us suppose, for the sake of notation, that the block IDX has 3 values. The last one is 1 because it's a 2D case, with BX blocks X and block Y, and thread IDX, thread X, thread Y. So you have a global index along X, which is given by the same formula used before. So I have to count the number of blocks that comes before, plus the offset within my block. And the global position along Y is computed in the same way. I have a specific number of blocks before my block, plus the offset within my block. Okay, I have a bunch of questions in here. Okay, let me see. Why the block size 3-to-1 and not 4-to-1? Okay, I have a question. Why the block size is 3-to-1, not 4-to-1? No, I started counting from 0. So in a way, try to I hope to understand. But the idea is that I go backward. When I have 4-3-1, the maximum indexes are 3-2-0 because they start counting from 0. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 0, 1, 0, 1. It comes from 0, like for the arrays. So that's the reason why I hope that's the difference. I mean, I hope I have replied to that one. But the same formula can work also for multi-dimension. The same formula, well, obviously, is again difficult to explain that, to understand that. But the response generically is no. So we saw this formula in a way. We saw this formula in a way. And now, actually, we are seeing equivalent formula for the 2D case and then for the 3D case. So the formula are not the same. They vary depending on the number of dimensions that are into play. And no, you have to, again, so the question is, do we need, can we use pointers to refer to, I think the question is, can we use pointer to refer to the host memory? No, because the host memory and the device memory are separated. So the GPU cannot access the host memory. You have to define something in the host memory, define something in the device memory, copy what you want from the host memory to the device memory, and then work on the global device memory. And then there are different sorts of memories. In this case, we just generically copy into the global memory. And again, to move backward, formula are not the same because you see in the 2D case, in the 2D case, those are the formula that allow me to compute the global identifier along the X and the global identifier along the Y axis, which imply that those can be used, for example, if I have to deal with pixel in a screen. So I move from those values to a bunch of 2 global indexes, the first one along the x-axis and the second one along the y-axis. But obviously I can transform those indexes into a single 1D case. that the global thread IDX, so is the global index of the thread within the entire grid of blocks. And the formula can be obtained from the previous one. I don't want to enter into the detail of that, but if you want, you can reason about that. So what is this? I try to explain what is this number. If I'm in a case like this one, and I am this thread, I want to know which is my order position within a theoretically linearization of the block within the grid and the threads within the block. That's the global linear index of each single thread. That can be used in the previous example to specify one specific element of the array that has to be summed. So in a way, if instead of specifying, as we specify in this example, a 1D grid, in this example we specify a 1D grid of a 1D block. If we move to 2D grid of 2D blocks, instead of the previous formula, that is, again, this one, we have to use something like this one, okay? To have the global position of the threads within the grid of blocks for a 2D case of 2D case. And what about a 3D case? Obviously, the most general case is to have 3D blocks, 3D grids of 3D blocks. And again, in this case, we can compute linear indexes, the global index along the x-axis, the global index along the y-axis, and the global index along the z-axis, which allow us to indicate a specific position within this matrix, like I have a thread in here, or you have a thread in there, or you have a thread in there, in a three-dimensional space. But after that, if I want to have, again, a global unique index in a linearization, complete linearization of the 3D structure, I have to use a more complex formula, which is this one, in which I also use the previous values that are those ones. Again, I'm not entering into the detail of those because it's difficult to understand, but if you want, you can reason a little bit about that and argue that, apart from possible mistakes I make, that should give you the global position of your thread within the grid of block of threads. That can be useful in this case. The transformation is useful in this case to move to a 3D data structure. And this transformation is useful to move to a 1D data structure while you are using a 3D grid of 3D blocks, using all the dimension, that is, you expand your power to the maximum admissible limit. Questions? One more question in here. Okay. What we are doing in phase 3. Okay, phase 3. Okay, move back. I have to move back to phase 3, which was phase 3. Phase 3 is the allocation of the array in the device memory. Again, it's written somewhere in one of the previous overhead. Let me look for that. Difficult to find it. I don't find it, but it should have been written somewhere. The host memory, so it should be clear by the diagram. The host memory is in here. It's one device. It's a chip. Okay, it's a chip with a cooler, and then you have another chip, usually much bigger, like this one. The modern GPU are this size, like thick like that, this way, and with another cooler, and you have the onboard memory. This memory and this memory are separated. From here, you cannot access there, and from there, you cannot access here. So in a way, in our program, we have to do twice the same set of operation in a way. What do I mean? I mean that we have to reply to that question, allocate the array in the host memory, allocate the array in the device memory on the GPU, and then transfer the content of the former into the latter. Transfer the content of V1 and V2 on the host to V1 and V2 on the device. Device V1, host V1. Is that okay for the question from home? Yes, we initialize, we save memory, we save dynamic memory in the device space, so we can copy the values, the data fields in there, such that the GPU can work with its own, working on its own global memory. Anything else? When you think about that, there was a question on projects, so I move backward. It's still possible to choose the project option. If you want, it's possible. So if you want to add yourself to the project list, do it. Again, do not underestimate the difficulty of making a project. I said that already several times, I repeat that. And do not postpone working on the project too much. Because I know now there is the summer session, so you don't have time to work at the project. Then there will be the autumn session. Then you start new classes, and so on and so forth. You end up in Christmas time without having work at the project. That's bad. Again, my suggestion is to work during the summer. Okay? Because if you don't work, if you fail working during the summer, then you get in trouble. Then you are of age, so you can decide to do whatever you like. But my advice is that, for example, last year, everybody was late. Many students worked during Christmas or in January, and they plead for having an extension in February to deliver the project 3 days after. And at the same time, they had their own examination, so it was too late. And that's why this year, in February, we did not organize the trip to Canelli, because everybody was too late, and I didn't know which one was going to participate. And the one who had delivered the project 6 months before in September, I didn't want to come anymore because too much time has passed. So in a way, the easiest solution is to deliver the project in September or October. And if you do that, if everybody would do that, we could organize the trip to Arol in November. That would be fantastic in a way. So who wants to come can come, visit the firm, having advice on courses, work, jobs, interviews, whatever. Anything else? Okay, one more question. How we know how much memory we can, I suppose, use, I don't see, use. There is something there. We can use in the GPU. It depends on the GPU. Initializing the GPU depends on the GPU. Like the number of threads you have on the GPU, it depends on the GPU. So basically, essentially, you should take a look at the characteristic of your GPU, so you know the number of threads, number of cores, number of the quantity of memory you have, and so you know how much you can push the the memory allocation. If you go beyond the limit, then you get into trouble, okay? Memory is, again, one of the main limitations for GPUs, because as I mentioned yesterday, the GPU memories are usually smaller than the CPU memories. Anything else? Okay, I think I'm done for today, more or less in time. See you, don't forget the lab tomorrow for the one belonging to Team B, and see you next Monday. We go on with some more feature, then we have just to clarify that, on Monday we go on with this a little bit, some extra feature. Then I think I will use one extra lesson in the last week to present some summarizing exercise. So 2 more lectures I'm gonna see, because again, it's the first time for me to present this topic, so I'm unprepared like you are in terms of, let's say, schedule and speed. I think 2 more lectures on CPU, on GPU, one dedicated to some theory, different sort of memory, synchronizations, optimization, and one dedicated to exercises, and then 2 more lectures on examination exercise, review examination rules, and then we stop. Okay? See you next Monday. Bye, everybody.